Welcome everybody to this webinar on flyback converter design. And we've got lots of people from all around the world. Hope everybody is staying safe and sound out there. And today we're going to try and have some fun in winding a transformer to see whether we can do that with the pressure of doing a webinar at the same time and thinking about what the design should be. So we're going to do the design, we're going to wind something, we're going to put it in a circuit, and if we're fortunate or skillful, hopefully it will work. So that's the plan for the webinar. So I think you can see two screens. You should see one is a picture of me and the other one is a picture of a winding machine, chuck and mandrel and bobbin, ready to go to wind our parts for a flyback transformer. So let's get started because there's lots to do here. I hope you've got your cups of coffee or mug of beer if it's in the evening for you. So when you watch me wind, you can have a beer and when it slows down a bit there. Okay, flyback transformer. Let's talk about that first. What's in a name? There's a lot of, articles you can read where people kind of got hung up about what a flyback transformer is called. And questions come up, is it a transformer? Is it a coupled inductor? Is it something else? And there's a lot of, people get hung up on naming conventions here, but it doesn't matter. On the schematic and in the industry, a flyback transformer is named a transformer. What it is electrically is something else. So in reality, it's a combination, and it has ideal transformers in it, ideal inductors in it, capacitors and resistors. So yes, there's an inductor in there, there's a transformer in there as well, capacitors, resistors, and if you were asking me for a pretty full model of a flyback transformer with two windings, it would have about 16 inductors forming the model. So it doesn't really matter what we call it, as long as we're all talking the same language. And in this industry right now, transformer is what we call a flyback transformer. Whether or not Faraday would agree with that doesn't really matter because language evolves. But however, from the design point of view, there is no confusion about the flyback. It's an inductor from a design point of view. And there's just one equation that matters when you're designing an inductor. And that is this one, which you can find on our website. The saturation level of the material, number of turns, area of the core, has to be greater than the inductance that you choose and the peak current that it's going to see. Now there's one qualifier here. If you're designing a flyback circuit, you always current limit, cycle by cycle current limit. Don't run it voltage mode, because then you don't have no control of the peak current. You can't design a transformer or inductor in this case from the design point of view. So just bear in mind, this is the only equation that you're going to see today. Actually, we're not going to talk about any other equations. This is about very practical work of designing and building a flyback transformer. And I was in this field a long time before I started successfully winding magnetics, because like many of you out there, you feel that somebody else has to do this for you. A magnetics expert has to do the design and the winding for you. Otherwise, you don't have much chance of it working. But we're going to see during this webinar that this is a skill you really need to bring in-house for doing your prototyping, because you can wind them very quickly, you can try different ideas very quickly, and you lose that ability once you go straight to your magnetics vendor. Now, this isn't any attempt, of course, to not use a magnetics vendor. They do a great job when it's time for production. But prototyping, build your own, you can go faster, you can try a lot more design ideas. So let's go to design. 2-switch flyback converter, 36 to 60 volts input, and 12 volt 2 amp output. And some of you who've been to our design workshops might recognize these specs that designed to. Now let's not do this as a PowerPoint. Let's go in and do this in our design software right away. So we jump into Ridley Works to begin the design right here. And here we see our 2-switch flyback circuit. 2-switch is a new topology in our software. We're doing a lot of industrial work right now, going up to 1200 volts on the input, and designing a flyback for 1200 volts input in a high ruggedness environment is probably not the best idea. So the 2-switch flyback clamps it, and it cuts down the stress on each of the switches in the primary. Apart from that, it's a normal flyback. It's just always limited to 50% duty cycle, but we find that most people design there anyway. So step 1, put in the voltages here, put in the specifications of the output voltage, and click OK. And then we go ahead and do the design. And we're going to up the frequency here to 200 kilohertz. As is a funny industry, we've been designing flyback converters at 100 kilohertz for about 40 years now. And despite all the talk of higher frequency switches, GaN, and all the rest of it, everybody still designs their flyback converters. So most people design them at around 100 kilohertz. Lots of reasons why they do that, but you'll be surprised the advantages you get once you start raising these frequencies. Going to 200, 300, 500, you know, whatever value you want to use, experiment with trying high frequencies. That's what we're doing here. Okay. And we're clicking our 2-switch flyback topology right here, which is already selected. Okay. And there we go. We've done the design in our program. So let's have a little check, make sure things are working properly. Here is my output voltage starting at 0, coming up to 12 volts regulation right there. Here's my output inductor, which is 47 microhenries in this case. Output cap is just about 400 microfarads, just a little bit short. Let's look at the important part here, which is the waveforms in the transformer or the inductor. So here at the beginning, we have startup where we're in current limit. That's the defining point. So that peak current limit is the defining point for how we have to wind this transformer. So it's very important to get that right. It's very important to control that properly. And then we go into regulation. Let's hit steady state there to continue. And we'll zoom in a bit on the waveforms here. And you can see our primary inductor waveform. So there's a step of about 1 amp at the beginning, and then there's a ramp of about 1.5 amps. Now this is all about the size inductor that we choose for our converter. And we're running in continuous conduction mode here, but it's not fixed that you have to do that. Around 24 watts, some people would design continuous mode, some people would design discontinuous. If you want to see discontinuous, we just make the inductor smaller. And there we see we start at 0. Now we have a discontinuous mode inductor, but our peak current has gone up to 4 amps compared to, let's reset the inductor to the first value, 2.5 amps. Which is the right design? Nobody knows. If you want to do a quasi-resonant soft switching, you would go to the discontinuous mode. The penalty, of course, is higher peak currents. That may be a good design point for you. It all depends upon your particular application. But we're going to lock it in right here with this value of inductance of 46 microhenries for working in continuous conduction mode. And let's move from the waveforms now, and we'll go look at the transformer design. So click on our transformer design page and turns and core. So this is how we go through the transformer design. It tells us at the beginning of this page, the approximate core area that you want is about 0.3 square centimeters. Now this is a trade-off of how hot is it going to get? What's the efficiency? Again, there's no right answer to this. We can go higher than this, we can go lower than this. And these are all the design trade-offs that we look at in doing flyback converters or converters in general. So one thing that I find is crucial to do is get fast at this, and then you can actually try lots of different cores. But we don't really care what core shape we use. We just want to know that that's the kind of area that you should be using. So let's go find a core that's somewhere near that area. Select core. And on our little test boards here, we have these EPC family that we can use. And EPC 25 is quite a big core. It's bigger than it's recommended. If we choose the EPC 19, that's smaller than is recommended. But I'm going to start there because just my experience tells me that looks about the right size. Okay, again, there's no hard and fast here. If efficiency is your thing, you'd go for a bigger core. If size is the crucial thing to you, you'd go to a smaller core, maybe even EPC 13. Go much smaller, and you try the design there. So it's very much an empirical part of the process here that we go through. You make it fast, and then you can go through lots of iterations. So we choose our EPC 19, click OK, and we see that's 0.2 square centimeters. Convention in our industry is you design for a maximum flux level of 0.3 Tesla. That will keep you out of trouble. It'll give you ruggedness. It'll give you headroom. So that's where we set it. That's where our industry has worked for a long, long time. If you're in aerospace, that's 0.25 Tesla. Some industries it's 0.2 Tesla. Okay, so it all depends on how much margin for overhead that you want in the system. If I design with 0.3 Tesla, we use our inductor design equation that says 22 turns on the primary and 11.47 on the secondary. And we know, of course, we can't do 11.47. You can only do integer turns, so we'll click on integer turns. And that winds us up to 23 on the primary and 11 turns on the secondary. We look at our core gapping here, and we can see it's going to be about a 10.8 mil gap. Sorry for the non-Americans. I've been here long enough that I'm used to mils. And that's 0.27 millimeters if you want it in metric units. Okay, that's the equivalent AL of the core. But we'll worry about that a little bit later. The first thing to do is to figure out how we're going to wind these turns on the bobbin. So this is our core. Right here, EE core, quite small. And this is the bobbin that goes with that core. It's a nice bobbin from TDK. It's got 5 pins on one end and 6 pins on the other. That always confuses our course attendees. They say, why is it that way? It's that way so you can't plug it in wrong into the board. If you have symmetrical bobbins, they can flip it on the board, both in a course and of course in production. So this is keyed to only go in one way. All right, now we're going to go to our primary winding. My software behaves itself. There we go. Primary winding. And it tells us, let's start with the simplest possible design is one layer of winding, one strand, and that would be a 26 gauge wire. My losses would be about 0.2 watts of loss. So it's like, okay, that's a less than a quarter watt loss. I'd got the size of this bobbin, seems reasonable. I'm going to stick with that for my primary. Now we go and look at our secondary winding. And it says here, if we wind the secondary the easiest way with just one layer, one wire, that would be a 19 gauge wire. So a computer program or an AI system will have no problem with that, but a human will look at this bobbin, and if you've got some experience, to say, you know, winding a 19 gauge wire around there is not going to work well. It's going to be really thick, and it's going to be difficult to get around the corners, and then it's probably going to bend these somewhat, you know, flexible pins on the bobbin if I try to wind a number 19. So I'm going to use 2 parallel wires. And that comes in with a 25 gauge. Notice the losses here, that's 0.24 watts. If I did the big wire, it's 0.21. So we're talking 20 milliwatts difference. So let's choose one that's easier to wind for us, and it's easier to wind for the manufacturer. So the primary was 1 strand of 26, secondary is 2 strands of 25. Well, I might even go simpler and say, hey, let's use 2 strands of 26. So we say with the same size wire all the way. And we give ourselves a little more margin for building up in the bobbin. So you have these options. Again, there's no hard and fast rule on all this. You could try many different design options here. So let's click OK on that. And we're ready to go and start to wind this. So this is where the fun starts. I'm going to slide over to my winding bench here, and you see we have an automated winding machine. It's got a little foot pedal on it. I push that, and it, oops, reset the turns. Let's go in there. This is how I'm going to do my winding. If you don't have a winding machine, you're doing this by hand. Of course, you're doing it because your budget is restricted. Should be one of the first things on your list. Get a good winding machine. It's okay winding one by hand or two by hand, but it gets pretty tedious after that. And your thanks, Tony, for the comment there. Oh dear, making me laugh. He's thanking me for being fully dressed. Yes. You will do that when you have your webinars. Okay, I do a thing here where I take my wire right here and I put it down on the floor. I put it down on the floor because it'll spool off, it'll come off the spool nicely as I wind it. You don't want to get any kinks in the wire. So I'm going to start here on pin 1 and wrap the wire around. And we set the turns count to 0, and then we push the button, and off we go. And as I go, I've been doing this for quite a while, so I'm quite good at this. I'm not as good as the professionals, of course, but you're trying to get the windings so they're all touching each other, but they don't overlap. You don't want to crisscross windings because that creates bulges in your transformer. So you have a little gap there. Push the gap down. And there's all different levels of winding machine, of course. This is a semi-automated where the turns count themselves and you've got a foot pedal. You can get automated feeds, so it'll automatically put the wires in the right place. Keep winding here. And we're at 17 turns. And now we're at 22 and 23. You always want to wind a transformer across the bobbin, finish on the other side if you've just got a one-layer winding. It's the easiest thing for you to do. It's the easiest thing for the manufacturer to do. So you make everybody's life easier, and then it costs you less money to make it. Cut those off, and I'm going to leave a little bit extra on the windings there because I'm going to use that for my test setup. What do you need next? We've got some tape, yellow tape, we call that. It's special tape. That's something you can go buy at Walmart. I don't know who sells this stuff these days. I get it from electrical insulation supply. I don't know if DigiKey has it or Mauser. You put your tape down. It's very thin, but it's good for several thousand volts. Now, we're not trying to put in isolation in this particular design. So why do we put tape in? We put tape in to give us a nice flat winding surface for the secondary. Otherwise, it's going to get caught on the primary turns. On goes the tape. And if I use this bobbin a lot, I would order the tape already cut to the exact size of the bobbin. Here I'm having to put 2 pieces of tape on to cover the width of the bobbin. So this is not custom slip tape for the bobbin. So that's our primary. One place there, and you make sure the tape is tight. Spin it around and show you. There you go. Wasn't too bad. All right, secondary. Now I've got 2 wires. This is a good idea when you're producing your magnetics, is to use 2 different colors. I've got a red and a green here. So when you put them down, you can see whether they've crisscrossed, and it's easier to count the turns afterwards. If you don't have a winding machine, that's especially important. So I'm going to go now. Last time I started on the left, and I finished on the right. I like to keep the direction the same, but because there's a flyback, I'm going to wind the secondary the opposite direction. So I'm going to start on the right and end on the left. Now you don't have to do it that way. You can do the flipping on the PCB if you like. But certainly when we're teaching, and just in production in general, I like to be able to just look at the transformer and I say, yep, that's a flyback, dots are opposite. I can see the windings going in the opposite direction, and then we know, of course, attendees have done it right. So when we do a forward, we wouldn't do that. We'd wind them in the same direction. And you lay the board out accordingly. Okay, so now we're going with our, whoops, I crossed my turns there, that wasn't good. Let's try again. Well, I didn't cross my turns. All right, never mind. Let's keep going. A nice Christmas color there, red and green. Be a little more careful with the bifilar. Cross them over again. Again, if you cross and you create space, you create leakage. Get a truly automated winding machine, this will be no problem. You can also buy bifilar wire where it's already glued together, so you don't have to. It's a little bit more difficult. Lots of wire companies will do that for you. So you can buy the red and green already bonded, ready to wind like this. So we're up to 7. 8, 9, 10, and 11 turns. Come up around the bobbin, wrap it down, and voila, there's the windings done. If I put them all in the right pins, soldering iron comes along. This is where you enjoy your cup of coffee. So I'm going to heat this, and I'm going to use the solder to burn through the insulations on the windings. And this is where quality of design of the bobbin helps. You want to have a plastic in the windings that doesn't melt with solder. When I started in this industry, that wasn't possible. It always melted the bobbin, so you have to be extremely careful.
What's the tape again we use? Polyester tape?
That's polyester tape, yep.
Number what?
Number what? Does it have a number? I have no idea.
Yeah.
It's one of the funny things, this tape. It's when you've been in the industry a long time, it's like yellow tape. Nobody really knows what it is, but it's 3M polyester tape. Does it have a name? Let's have a look. No, it doesn't have a name. It doesn't have a name, but you call up a magnetics company or an insulation company, you say, hey, I want yellow magnetics tape, and they know what you're talking about. But yeah, it's got a proper spec. And when I'm doing design reviews from people, I want to know what the tape is made of, who's making it, the quality and everything else, and the temperature rating of that tape. And we're melting through the wires. So these are solderable wires. Makes that construction a little bit easier. And you can get all kinds of solderable wires. And I don't mind using a solderable wire in this application because if it fails, it just shorts the primary or the secondary and your converter stops working and there's no danger. I do not like using solderable wires for triple insulation. I know a lot of people do it, but I don't want a fault in my converter that gets the temperature up to 130 degrees and then maybe kill somebody. That's probably not a good idea. So you put a bit more money into stripping the wire in that case. Taking a little longer to burn through this time because we've got 2 strands to burn through. A little bit more conduction away from the soldering iron. See the smoke coming off. Looks good. And then we're going to solder the other secondary pin. Now you have to be very careful on these bobbins because the pins I'm soldering to are the same ones that plug into the board. So you want to try and keep them clean. So you keep all the solder close to the bobbin. Okay. So there we go. I'm going to snip off the secondary leads like that. And my primary has a soldered bit I can put in my tester Let's put it on the other one as well. Okay. Got it. Okay. Pull that off the bobbin without breaking it. Okay. Thanks to Renko, by the way, who make all these mandrels for us. We teach our course. Hope there's somebody out there from Renko. Okay, so here we go. We built that transformer. Second layer is the green and red. I don't know if that's in focus or not, but that's all there is to winding that transformer. Do I need another layer of tape on there? Well, it doesn't do anything except make it look pretty, and it also keeps the heat in. So there's no need to add that second layer of tape unless you want to put labels and other things and just want to make it look like a neater component. But I kind of like looking at the wires, quite honestly. All right, back over here. Once I've wound this, the next thing I do is I put it on a frequency response analyzer. So we're going to measure magnetics impedance.
Use this setup to measure magnitude and phase of magnetics impedance.
So here's our test setup. You can see that we put the transformer under these two pins here, and we're hooking up to this Ridley box, which is going to measure it for us. And let's put that right under there. And the first thing I'm going to do is measure the air core. Just an air core. I've wound 22 turns on there, so a little bit of area to it, so it will have an inductance. Let's go see what that looks like. And sweep.
Sweep initiated.
And you can see there it's sweeping the impedance in gain and phase. I always start with the gain phase curve because I want to see this curve that comes along and goes up to a peak, and then look at the phase and make sure there's no kinks in the curves. You know, if you've got winding shorts or things like that, and you look at the phase, you look at the gain, you'll see some unusual characteristics in there. So I always start with this gain phase curve. I'm not directly measuring inductance at this point. So here we go out to 20 megahertz. If we look at the inductance, we can change the scale.
Test setup to measure magnitude and inductance value of magnetics.
We see right now it's measuring 2.5 microhenries or so. So let's move the cursor along to here. 2.5 microhenries. Why is that so low? Well, we don't have a core. Let's put the core in. Now we're adding a core. Sorry, I can't see this on your camera. And remember, our goal here was 47 microfarads. Let's measure that again.
Sweep initiated.
Now we're measuring the same core again. And you can see what's happening here is we've got, oops, hold on. Let me stop that.
Sweep cancelled.
Let me sweep without the core again. This is nice to collect all these measurements. Let's sweep again.
Sweep initiated.
Okay, so I'm going to save this data set as the air core. So that's my baseline. Okay, if my designed value of inductance were 5 microhenries and I'm already getting 2.5, I would worry about that as not being a solid design. You want to be well away from the air core value. So let me go and add the core back in now.
Sweep complete.
Right there. Let's sweep again.
Sweep initiated.
I'm going to hold that core together because it tends to drift apart if I don't do that. So now you see I'm getting about 500 microhenries. So this is the core with no gap in it. So I'm moving this inductor value around from the air core, which is the minimum, 2.5 microhenries, put the core in, it's gone up a factor of 200 times with the core in place. And of course, that's way too big.
Sweep complete.
Okay, save that as data set 2. That's core, no gap. Save that one. All right, now we want to put a gap in this core. So people really worry about the gapping as well. What size gapping should I order? Should I get bale of this and that and that? Order your cores ungapped. Go back to Ridley Works, and if you looked at our first spec here, it said 10 mils. Okay, so I'm going to come over here to this other camera. Hopefully you can see this. Set my core in there, and I want to put a 10 mil gap in this core. So you have options of how you do this. One option is to grind it. So you can get some sandpaper and grind that center leg down to 10 mils. That's messy and imprecise. It's hard to keep it flat. So what I do on my prototypes, and this trick in industry, is I just put little gaps in here, little gapping material. And this is a sheet of paper. And Americans out there, a sheet of paper, a ream of paper is about 2 inches. That's 500 sheets. So each sheet of paper is about just a little over 4 mils. So I'm going to put, there's one sheet of paper in there. I'm going to put 2 sheets of paper in here. And we do this empirically. You gap until you measure the inductance that you want. So don't look for complicated formulas on inductance. You know we need approximately a certain amount. So you try that and it won't be precise. So then you grind it to a different depth, or you apply a little bit more gapping material until you get the value that you want. And that's exactly the way the manufacturers do this. They grind down the center leg until it measures right. It seems a bit hit and miss, but it's engineering. That's the way it works. Okay, so now we got our gap. We put the core back together again. If we're lucky, we'll hit the value. Okay. And let's sweep one more time.
Sweep
Gap
initiated.
core. And hasn't hit the measurement frequency yet, so we're not reading out what it is yet. Oh, our cursor's over there. Let's move the cursor over a bit. There you go. We're at 44 microhenries here. We wanted 47. Am I happy with that as a prototype? Absolutely. When I go to a manufacturer, I want that plus or minus 5%. When I'm doing a design here and I'm trying to quickly test out my circuit, if I'm a little bit low on inductance, I'm okay. That means I'm a little bit low on the Bmax that the core is going to see. If I was a little bit high on in the inductance, I would be a little bit more careful. But that's good enough. Again, it's not rocket science, folks. It's magnetics design. And you know, if you ran the simulation with a 44 microhenry versus a 47 microhenry, you really wouldn't see any difference. What am I doing now? I'm putting tape around the core here to hold it together. Same yellow tape because I know it's got good temperature rating. I'm not using core clips. You can buy core clips for these, but if you put a metal core clip next to a gap, it's going to get hot. So we don't clip them. And people don't tend to use the clips in production either, because that will, it's easy to break the core when you use a clip. Plus it creates a conductor between primary and secondary. You just got metal where you don't want metal. So people use epoxy, they can use tape, they can use all kinds of constructions for making these transformers work. Okay, so what am I going to do now? I'm going to put this in the circuit. So let me pull off my camera here. And you can see our little test bed that we've got. These are our new course boards. Some of you have been to our course, and we've made these boards thicker, more rugged, simpler, and nice gold sockets in. This is just waiting for a flyback transformer to be plugged into these sockets in the middle. And we've laid out the pins here and the sockets to take up to 4 different transformer sizes. So we've done converters on this board anywhere from, you can go as low as you like, but we've gone all the way up to 400 watts. Got a 400 watt flyback on this board and a 400 watt forward converter on this board. Switches on the primary. Let's see that red board there. That's my friends at EPC. They designed a 2-switch forward or 2-switch flyback board for us there. So we've got some nice fast switches in our device. Let's see. Let's plug this in the converter. Right, those sockets there. Come on. All right, plugged into the board. Everything's good. And let's see if it works. By the way, let me save that third trace there. Data set. So this is core with gap. Save. Now, anytime, everything is linked together in our Ridley box design system, we've got the Ridley Works designing the transformer, we've got the frequency response analyzer here measuring these characteristics, and you can run this data back over to Ridley Works and compare. Oops, let me turn on my trace first, sorry. We have a little thing here where we have to
You are using current mode control.
Turn on the measurements. There they are coming in. Back to the transformer, primary impedance. And you can see here the green curve is leakage inductance. The blue curve is magnetizing inductance. That's the one we were trying to hit, that 48 microhenries. And the purple curve is the measurement. And you can see we put the measurement right on top of the blue. The predicted resonance, that was predicting about a 10 or so picofarads. You look at the measured capacitance primary to primary, it's just 5 picofarads. So we have a very simple test setup here, but we have very fine resolution of capacitance. We can go all the way down to under 1 picofarad. So you can see changes in the transformer winding layout and to see how well that's going to work. So we see that resonance. This resonance in the measurement is at 10 megahertz. We're switching at 200 kilohertz. So we should be okay with that. All right, let's look at, we didn't measure the leakage. Let's go measure the leakage now. I'm gonna pull this out of my board, sorry. I'm gonna pull it out. So here's my transformer. So we're gonna put this back into test, but then I'm gonna short my secondary. So I'm gonna put a wire across the secondary to short it to measure the leakage. All right. So we go to our little test box. We say, let's measure the leakage inductance.
Use this test setup to measure leakage inductance. Remember to short the secondary.
Okay, put that little memory in there just to remind you to short the secondary. Sometimes you got a lot of secondaries and you forget. There's so many things to measure on these converters. So same test setup, but we put the short across the secondary. I'm just going to hold a piece of resistor wire on the secondary. Normally you can't do that, but these are fairly high turns count. So, the little bit of extra impedance of me placing it on there is not going to make a difference. If you've got a big step down turns ratio, you can't do that kind of thing. So let me place that on there. Now we're going to measure with totally different parameters this time. So I'm not going to use the same scale. So I'm going to get rid of those old measurements. Clear that. And then we're going to sweep again for leakage.
Sweep initiated.
Okay, so you see my leakage starting out around 1.2 microhenries. And then right around 100 kilohertz, it's starting to drop. Okay, it's kind of 10 megahertz. Now
Sweep
we're at,
complete.
okay, there you go. So that's the leakage inductance of this transformer that we just wound. And let's run our cursor across that. So we start at the max value. It's not max, that's min. Oh, sorry, it's going, not for going for the max value, let's go for minimum value. Over at the left here, we see this starts out at 1.1 microhenries. And then, clicking right with our cursor, we see this down to 1 microhenry at 129 kilohertz. 200 kilohertz, which is our switching frequency, it's down to 0.9. At 1 megahertz, it's down to 0.7. And at 10 megahertz, the leakage has dropped to 0.53 microhenries. So we got a 2-to-1 drop in leakage with frequency. I don't know any manufacturer that gives you this curve, and I wish they would, because this curve tells me so much. It tells me, hey, look here, this is where the leakage starts to drop, right at 100 kilohertz. That tells me I've got proximity losses going on. The currents are shifting towards each other. Doesn't mean it's a bad transformer or anything, but it's telling me something about the transformer. Giving me one value of leakage. I mean, where would you put the one value? Put it there, put it there, put it there. It's a 2-to-1 range. Gives me no quality control over this transformer whatsoever. So when I do pre-production runs, multiple samples, then I get parts back from the vendor, I run them all through this curve measurement, and I expect all these curves to be right on top of each other. They should all have the same characteristic. If they don't, they've changed my design. Okay. I know there's lots of magnetics vendors out there. Please, next time I order one for you, measure this for me, because the first thing I have to do when they come in the door is I have to measure it again, okay, because it hasn't been done. So I like to see this leakage inductance versus frequency. This is just a portrait of the magnetics. You can tell it's wound right without having to take it apart. So that's what we're doing right there. Okay, so now this has got to go off the test setup and back into my circuit again. Okay. I'll plug it in. There we go, back in the circuit. And let me grab my camera. Sorry, the camera's just looking at the ground there. So now I plugged that magnetic into the test bed. You can see it right there. So it's quite small. You know, if you're trying to design a high density 20-watt flyback converter, you know, I've got lots of capacitance on the input, lots on the output. Some of that could certainly be removed, especially if you used MLCs. We make our switch card and diode card bigger than they need to be, because we can test transformers here up to, you know, pretty high power levels with these devices. So that's the transformer in place. You can see a current transformer on the board there too. I'm used to doing high power, so I do a lot of current transformers, not just sense resistors. So that's what that is doing in the circuit. And then of course this is our control card for the board. Let's go look at our waveforms. So we're going to disconnect
Ridley box disconnected.
the, sorry, oh, right. Here we go. We'll look at the circuit. So if any smoke comes out of it, you're going to see it. This is brave of me. Never let anybody see your circuits blow up. Can you see that? Not really. Okay, there we go. Transformer in place. Sorry for the bad taping job there. I would do, in a better design, I would have used a much thinner tape that wrapped around the bobbin so that you wouldn't see all that ragged tape on there. But we're trying to go fast here. So now I'm going to turn on my scope. Same box. It's all in the same box. You have no idea how convenient that is. Having these all linked together just speeds things up amazingly. And this is our gate drive waveform. And you see, well, it's really, really nice and clean. Don't believe that for a minute. So let's make sure the bandwidth here, it's got a 3 megahertz bandwidth on this. Let's turn that off. So now we're going full bandwidth, and we want to do ±2, and it's a ×10 probe. Should have set this up ahead of time. No, it's okay. ±20 volts. Okay, so this is the gate drive coming out of our chip. Now we're going to send this in to drive some GAN devices. So we've got to divide that 10 volts down to work. I think we've got TI drivers on the board to drive the GAN. But we see we got a nice, it's just a little bit slower than 200 kilohertz here. But our design processes always allow for some margin on frequency to make sure that's okay. So now let's put the probe on the drain of the FET. Okay, and start turning up the voltage. And here you can see the FET waveform, and things seem to be working okay. Which means that transformer is good. We're at 20 volts on the input. Lights have turned on my load. Let's go higher on the voltage here. That's 50 volts. And we're at 30, just above 30 volts now. And now you can start seeing the duty cycle changing. And you see we've got some work to do on snubbers there. There's an interesting bouncing around with this topology. You see that low frequency bounce there in between? This is the midpoint of 2 transistors which are off. So just a little bit of twitching on this ring cycle, and they end up in different places from one cycle to another. This is not necessarily an instability. So I see my leading edge, he's jumping around a bit too. Oh, sorry, the leading edge on the, let's see, I should be trimming on the fall to avoid that. Okay, you see this edge here and that edge there and that edge there are not moving. So that's my clock pulse. It's okay, right? So, that's something we got to work on in here, but all the way up to 60 volts. That looks like it's just bounce around when it's first coming into regulation, actually, which you'll all be familiar with. Somebody asked a question actually on our group the other day, how do I stop a converter from hissing? Flyback converters from hissing? When it does this kind of thing, and there's that chaotic operation going on, the noise you hear is hissing. Even though it's switching at 200 kilohertz, there gets a low frequency component in there. You may hear that. I can hear a little bit of hissing in this one, but then when it cleans up, it goes away again. Okay. Need a snubber on here. That's all part of our lab work when you come to our course. Plus or minus 100 volts here. The voltage rating of these FETs is 100 volts, so we're well below that. Because it's a clamped 2-switch forward, this voltage won't go above the input line, which is 60 volts here. So you can see we've got a nice clean design there, except for that little bit jumping around stuff that we need to clean up in there. And I think once I've got the snubbers going the board, that would go away. So this ringing noise here, I see a lot of flybacks. People design them without snubbers in because they want to get their efficiency numbers up. This is exactly what happens. That becomes RF noise, gets into the controller, and it starts affecting the clocks and things like that, which causes that kind of jumping around. So that's what your snubber can help you with. Okay, so there we go. So we did it. It was a bit nerve-wracking. Let's go back to the PowerPoint here. So we've gone through and we've designed this flyback transformer, and we wound it, then we tested it, and then we put it in the circuit. And some people have said, well, this isn't good. I don't want your design program because you're taking all the fun out of this. What is the fun? The fun is building that creative for a circuit. Okay, so winding the transformers, doing that, and people like to take their time doing that. But I would propose something different. When I do a design like this, if this were a real production design, you've all seen now I can wind the flyback in what, 15 minutes, make it work. I can do the design in 5 minutes, and that's while talking to, you know, 400 or 500 of you at the same time. You can put out a transformer in 10, 15 minutes. And what I would do for a production design here, I would wind, in one afternoon, I would probably wind 20 different versions of this transformer. I would try it on a smaller core. I would try staying on this same core, and I would use, instead of 2 strands of secondary, I'd use 1 strand of 19, but I'd use a Litz wire for that one. So another variation there. I'd try another variation perhaps where I do the secondary first and then the primary afterwards. So you can try all the different permutations of making this transformer. You can try doing, okay, this was continuous mode. What if I wound one for discontinuous mode? What's the efficiency going to be if I go into discontinuous mode and I manage to get, you know, valley switching in there? But you now with the design tools here, instead of agonizing over the design, which is really quite easy, and everybody in magnetics knows that these flyback transformers are really easy to put together. Now you can just open up your horizon and say, okay, how can I creatively rewind that flyback? This one is very easy, that there weren't a lot of options on the primary, and there's only a couple of options on the secondary, but when you get a 4 output flyback, now you've got so many permutations. So when I'm doing multiple output converters, you know, you're really worried about how is the cross regulation going to work in this converter, and you really don't know until you start putting them in the circuit and all these interactions happen, all these ringings happen, then you know what your regulation is. So you just build transformer after transformer until you get the one that does the best job for what you're trying to do. So you want to get quick at doing, you know, this part of the process. And then, you know, your design life is a lot of fun. You can spend just as much time as you always do on this design phase, because we all know this is the creative stuff, this is the fun stuff. You know, next you got to go to the proper layout and bills and materials and production and the tedium that goes with power converter design, the thermal measurements, everything else. Loop gain is fun too, measuring that, designing that. But you do a lot more iterations. You try a lot more variations now that you've got this high-speed design process in the way. Now we've got some people on the webinar from the mags companies, and you know, they'll say, yeah, we can wind those for you, we can do it fast, but they can't do it in 10 minutes. You know, they might turn around in a week for you if you're one of the really good customers, but that's a week instead of 10 minutes. So in that week, you could have built 40 transformers of your own with different variations. So you work with your vendor and saying, hey, I'm trying this, is this a good way to do it? But you do all this experimentation yourself, and then you hand it over to the vendor and say, okay, just build this properly for me because I know I can't do this. Or some companies, you know, they've got production people on the floor. It's like, well, that doesn't look that hard. Let's get into the magnetics business. And if you're only building a few hundred of a specialty item, you know, why not learn what it takes and, you know, bring that process in-house? And then you've got full control of it for the future. It's very nerve-wracking to be buying, you know, a magnetics part from a vendor that, you know, you're trying to save some money perhaps, but what if they're not there in 2 years? What if you don't have all the specs on how that was built? So there's huge risk in just turning over the magnetics and not getting the full details of the design. Lots of people that come to us for consulting help, they say, well, we've got this converter. The company that made this for us 20 years ago is not in business anymore. It might be military, aerospace, or whatever. We don't know what's in it, and they're stuck. I mean, without the magnetics, you're completely stuck. So, you know, bring that process in-house, make it, you know, a skill set that you have, and then work closely with your vendors to build the way that you want it built. And then, you know, you've got a much more rugged product when you do that. Okay, we've got. I'm going to answer some questions in just a minute. Let me just show you. I think a lot of you out there are familiar with our program right now. Somebody asked us, you know, so for this design, we've just done our design here. You know, what is the efficiency going to be on this converter? So let's look at our efficiency. And you see here it's 36 volts input, 12 watts output, 24 watts. It says we're 86% efficient. Like, well, what's the efficiency down at Highline? So what you do is you go to the waveforms, click on the waveform, and you set the line to 60 volts in, and you run that again. Okay, so it reruns the simulation into steady state. It's a very fast simulator, but you see there's a little bit of a tedious process here. And now the efficiency has climbed, in this case, to 87 with that. So one of our customers asked us about a month or two ago, can you automate that process? It's like, yeah, sure. But for now, you're going to have to do it by hand. But we kind of thought about that. We built, you know, the world's fastest simulator into this program here, and we're not really leveraging that by automating this and looping through it. So we took a shot at doing that. So we go to multi-sweeps here, and we click on efficiency sweep. This is brand new. This will be released next week. So if you have our program, you don't have this yet, but you just click go.
Simulating efficiency.
All right.
36 volts. 100. 90. 80. 70. 60. 50.
So every step
40,
in efficiency
30,
here, we are
20,
simulating 1600
40
cycles.
volts.
It's interesting.
100,
The voice on here is
90,
reading volts as VOLTS.
80,
That's the first time it's done that.
70,
But every step here is 1600
60,
test cycles, and we're going through
50,
30. So that's
40,
30. That's 480,000 cycles of closed loop
20,
simulation we're doing here. That would probably
10,
be a few
60
hours if you did it on LT
volts.
Spice.
100,
PSIM would do okay on that,
90,
but nothing's quite as fast as ours
80,
here. So we're running
70,
through this.
60. 50. 40. 30. 20. 10. Efficiency
Wonderful.
calculations complete.
There you go. So now we have these classic curves that you'll see in the data sheets. This has just run a full simulation of this converter, gotten it into steady state. It includes proximity losses on the transformer and inductor. There's great detail in here, and he's just swept 30 points through here. So that saves you a couple of hours in generating those curves. So I think you're gonna like that feature. I really like that we did this. We're starting to do a lot more of this. We're pulling away from the hardcore simulator, saying, okay, what if we loop this and this and this and do a lot of, you know, variable analysis of the converter. So we do that for the efficiency, and then of course we do that for the loop gains as well. Here's all the different loop gains for this. It's not for this particular converter. We can run that too. Let's run that.
LOOP1, LOOP2,
LOOP.
LOOP3.
She has ceased to be able to read for some reason.
LOOP5.
Must be a Windows update.
LOOP6. LOOP7.
That's funny.
LOOP8. LOOP9. Multi-loop calculation complete.
So these are all the loop simulations for this converter that we just designed. Okay, so that's kind of cool too. Saves you lots of work. Generates for you people in aerospace and military and so on, generates paperwork faster than you can imagine. So you can do lots and lots of curves like this, make it look like you've done a huge amount of work, which of course you have. Okay, but you're just much more efficient at doing it. Frees you up for the creative stuff, you know, get the bread and butter converters done fast. Then you've got time in the lab to explore, you know, should I be looking at quasi-resonance? Should I be looking at LLC? Should I be looking at some different kind of topology for the future? So hopefully this frees up your time, you know, on these normal converters so that you can go look at other things in your job.
Quickly go back to the magnetics designer and show the losses. I know we did it on the previous program.
The losses.
Show where the losses were in the magnetics.
Okay. Somebody wants to see the losses in the magnetics. So we'll go transformer design and started here. This is where we just chose the primary turns, secondary turns, and the gap. No losses on that page. And then we go to the core material. And we have the option here of changing different materials. So there's an F material, 0.2 watts, R material, I think that's better. 0.17. I think we used a PC95, 0.17, PC90. So you got about 0.2 of a watt inside the core. We're going to do a webinar soon that talks about how we do this and this model that we generate. This is a SPICE model. We did very quickly, but I was going to devote a whole webinar to the core loss rather than just a quick, you know, pass on that, because that's kind of cool what we generate there. So that's the core loss. Then we go to the primary winding loss. And it tells you here, this is the winding loss if you don't do proximity, is 0.073. And then if you do the winding loss with proximity, it's 0.118. Now I've changed conditions here. This loss always refers to my latest simulation. Okay, so if I set my line back to low line, it'll change. So we have this built-in simulator. These are not just calculated losses, we simulate, because you can't have closed form equations for anything in a converter, not even duty cycle. There's so many things that get involved in duty cycle. We run a simulator, then we analyze the waveforms. And that's what we use in our design pages here. Okay, so now you see that's up to the 0.2 watts that we had before on the primary. Secondary is 0.2 watts there. Now this is a calculation including the proximity. So when I do those efficiency curves, it's including this. If I don't include the proximity, it's, you know, like 30% less than that in this particular case. We can dig in deep and we can go in and sweep the AC resistance if we want to and get the curves of AC resistance versus frequency. That's, well, we'll do that while I'm talking here. We'll have that run.
Solving Dowell's equation for transformer secondary. 10 kilohertz.
Okay. John, any more questions you got flagged there?
That was
1
it.
megahertz.
I've
Okay.
got some red flags for
10
you if you want to talk
megahertz.
about some other subjects.
Solution complete.
Okay, so this is where we plot the winding resistance versus frequency, and then we fit an RL model on top of that. So there's the RL model. So here's the model of our windings for doing proximity loss. So you can dig into this as deep as you want to. Okay. If you to do, I'm sorry, that was the secondary. I think I just swiped. Not sure. Yeah. Okay. So there's your losses. So we go back to the schematic and we look at efficiency. It summarizes those. So the magnetics winding loss was 0.4 watts. The core loss was 0.1 watts. Remember that changes with the input voltage. Okay, so you're going to see these things moving around with input voltage, output voltage. Be kind of nice to run through that sweep. You know, this would be really easy to do. Is let's find the loss in the magnetics at every test condition. So we could do another set of curves and find the worst case for the magnetics. It's a really good idea now I mention it, because it's quite easy for us to do that. Snubble losses are in there. That will change with test conditions as well. Switching losses, conduction losses, all these change, all these components change, and we can break all of these out, you know, if anybody wants that. Okay, somebody asked, why do we check the input inductance but not the output inductance? Well, we always check the inductance on the highest turns count winding, because that's where you've got the most resolution. So if you've got a step down transformer, you just measure it on the primary. If I measured it on the secondary, it would be the same value divided by the turns ratio squared. So you don't need to measure both. You only need to measure one. So we measure the one that is the bigger value and the easiest to resolve. So it's just redundant to measure from both sides of the winding. Okay. Acme ferrite core materials. Is there really an Acme ferrite? Know that we use Acme as one of the vendors in a cartoon strip, and it's out of the Roadrunner, right? Acme, this and that. We can do any ferrite materials anybody wants us to do. Our interest from magnetics vendors thus far in modeling core loss has been 0. But when you look at the core material here, we're quite happy to add anybody's material, but they do have to call us and they have to provide data to us. Okay, it's no good just hand waving and saying, well, that program doesn't do our material. It's like, well, nobody's ever asked. So we can easily add core materials here. If you've got some you want us to add, we just ask you to look up certain loss points on the curves. That's all there is to it. So it's very easy for us to add curves here. We're kind of waiting for magnetics vendors to kind of get on board with the stuff, but it's not happened yet. I guess they're busy. So, you know, they've got their own ways of doing things. But yeah, we can add anybody's core material, but they do need to get in touch with us if they want that done. Okay. Somebody asked, I noticed, you know, what about a toroid for lower leakage? You don't normally use a toroid for a transformer, because you've got to get coupling between primaries and secondaries. And as you bend around the corner, you cannot get them that repeatable. I'm not saying it's never done, it's just unusual. And it's all about winding placement when you're doing cross coupling between windings. It's not about low leakage, okay? So the toroid just really isn't a good choice for doing flyback transformers in general. Now, if you've got a one-to-one winding, it's good because you can wind it bifilar. And then a toroid does a lovely job and it gives you low leakage, but of course it's more expensive to wind it. So every case is different. Sometimes, you know, we might look at a toroid. Some of the aerospace customers want a toroid. So it's like, sure, but let's try and range the turns count to make it a nice integer that we can wind bifilar or quadfilar and then connect, you know, series parallel to get the turns counts that we want. So you can do that kind of thing. Yeah, hope that answers it. Webinar on coreless transformer designs. That would be the transmitter webinar. So if you want to, if you want to know about coreless transformers, go study transmitters. Okay, if you're doing a power supply, not a good idea. Many have tried it. Fin6 was the famous one. We're going to do a coreless transformer at 50 megahertz, right? So they build themselves a transmitter at 50 megahertz, and then they put the core in to make it a non-coreless design. Secondary leakage. It's the same as the primary. There's one parameter between the primary and secondary. There's no point measuring two values. In our snubber design, we refer to the secondary. So we've got primary leakage of 0.4. Secondary leakage, we say calculate it from the primary. So we've got a 2-to-1 turns ratio in this case, I guess. And that's the secondary, that's the primary. You only need to measure one of these. Which one do you measure? The higher one. It's hard to measure 100 nanohertz. Just lead inductance is going to start adding in significant contribution above that. So you always measure just the one side. Other questions?
They're asking what's the difference between this and compared to
Frequency. There's no difference. I mean, a 60 hertz transformer and a 200 kilohertz transformer is the same process. You've got to obey the saturation thing, but 60 hertz transformer is a transformer in general. It's not an inductor. Okay, we're designing for an inductor here, but you know, we don't switch at 60 hertz for high density electronic power because the size is enormous. You know, a 30 watt transformer weighs about 2 pounds. For this application here, it's just a big thing, and it would cost more money than the entire switching converter would cost. So, but the process is the same. You know, all the things we've done on proximity loss, that was originally done for 60 hertz work, for utility work. So Maxwell is Maxwell, and you know, everything Faraday did was the same at 60 hertz as at 200 kilohertz. Just different frequencies, different dimensions, but it all comes out the same in the end. What's that? Different materials. Yeah, you probably wouldn't use a ferrite because low frequencies, your core losses are going to be less. So you're using, you know, steel, you know, laminations of steel, higher flux density on that. Yeah. Okay. Is there a fundamental way to measure the primary inductors? Yeah, we showed you how to do that. You need a frequency response analyzer. Okay, I mean, I don't know how anybody designs without a frequency response analyzer because it's kind of pointless. When I was in school, you know, the early 80s, you made your own frequency response analyzer. You had a signal generator, which you can get in a scope now, and you just plot the waveforms. So you measure inductance and leakage inductance by sweeping the frequency. Otherwise, you're leaving 95% of the information on the desk. You're just not getting the job done. So, you know, learn how to do that. And we have app notes on our design center about how to measure, you know, the impedances of transformers, leakage and everything with, you know, if you have to do it by hand. And then after it takes you an hour to plot, you know, you start thinking about investing in a tool that'll do it for you. So we got that for you if you need that. But
so is there a practical limitation on frequency for flybacks?
Is there a practical limitation on frequency for flybacks? Yes. to answer the question?
Yeah.
Do I know what their limitation is? No, I don't know. There's people doing megahertz flyback. Go look at the material from Dan Jataru. He does, I think, 1-2 megahertz flybacks, and he does 0 voltage switching and nice planar designs, you know. So there's no reason you can't do a couple of megahertz if you want to. Do you gain anything? Well, often a flyback has to have safety isolation in it. As you shrink down, you know, it doesn't keep shrinking. You know, core losses start to climb, other things start to climb up. That most of the world is stuck below 130 kilohertz because they have this thing that they can't go into the higher EMI band. It's like, but half the world's realized, well, we can switch higher. The filter components are smaller anyway, and we just do the design better so we don't generate so much noise. So what else limits it? Well, the control chips. You know, it's hard to get a control chip that's happy above a megahertz. You know, if you're using a micro to control, you know, you got to make sure you have the resolution. But the gains you get above a megahertz or two start to diminish fairly rapidly. Okay. You just have to look at the Vicor products to see that. But you can keep going with the flyback. It's a good question, actually. We should go build a megahertz megahertz flyback transformer here, John. And by the way, John Beecroft is answering all your questions for you, and he always helps us on these webinars. Thanks, John. Thanks, Denise, for setting it all up here. What else? What is role impedance measurement in leakage inductance? Well, you saw that. That was right here. Up. There you go. This is the leakage versus frequency. It is not possible to wind a flyback transformer on that same core and reproduce this unless you wind it the way I just wound it. So this is the fingerprint of the transformer. We talked about this in an earlier webinar. Okay, this is an important characteristic of that transformer. And then, of course, on the primary, this is an important characteristic. Exactly where it resonates, exactly what the shape of that curve is important to know. You know, this is magnetics 101 to me. If you're just getting into magnetics, just start measuring impedances right away, and don't look to the vendors for guidance on this because they only give you numbers. They give you magnetizing, they give you leakage, they give you resonant frequency. They don't give you curves. Some of them I know internally do sweep the curves, but they won't generally give you those, you know, unless you ask for it specially. But we always do this. It just, you know, it's just second nature to me.
They give you curves for EMI.
They do give you curves behind it. The leakage goes down with frequency. Is that a benefit of switching at higher frequency? No, not really. It just is. I mean, that low leakage doesn't.
You see the last question?
I'll get to that in a minute. What was I saying? Okay, when you've got that frequency versus leakage, you've got to use the leakage value at the right point. So if you're designing the snubber, the 10 megahertz snubber, you want the leakage at 10 megahertz. If you're trying to calculate 1/2 Li squared, well, you should probably use the leakage at 100 kilohertz. And then if you're trying to do something about, well, what's the value the manufacturer gives you, they might give you the 10 kilohertz, you know, but these values are all over the place, 2-to-1 range in difference. Somebody asked about the Ridley box or the AP310. The Ridley box, it says it seems more capable. It's not really, it's just that we're pairing Ridley Works, which is doing all the design, with the Ridley box, and it just flows seamlessly because it's in the same box. Notice that within Ridley Works, we also have the AP. You can click on that and you do everything the same for the AP. So if you're military, aerospace, you need rigid rules on calibration, you need mil specs, it's the AP310. It's still, you know, the Cadillac of the industry, or the Ferrari or whatever. It's got high power output, it's got the bigger frequency range, it's got very low frequency operation. The AP does it better than anything, and we tie that into our software the same way. Not everyone can afford one of those. They're 14K, so getting the Ridley box with the software in there as well is, you know, a better option than buying something that's just a frequency response analyzer at that price, and there's, you know, plenty of those around. So we're providing a whole design environment here, but it's happy to work with the AP the same way. Does all the same thing. Here you can see, you can measure plant, you can measure leakage. Everything is set up exactly the same for the AP as it is for the frequency response analyzer inside the Ridley box. Another important difference on the AP is that the inputs are not grounded. So when you're doing, serious research into complex magnetic structures, you need to separate grounds. So we have to work a little bit harder with the Ridley box because everything is grounded in here. So you may lose a little resolution there. And then, it's mostly really about, do you need the mil-cal, the everything else, a lot of companies, you have to have your equipment calibrated to be a frequency response analyzer. And it's just paperwork, and that will take care of it. You get a much bigger signal out of the AP as well. So, if you're in a high-end company and you're doing research, go for the AP. If you're trying to measure loops, characterize inductance, you're a magnetics company, go for the Ridley box. It'll do the job for you. But they both work with Ridley works. So they both are a complete design environment. Hello, Professor. What's that? Oh, you're answering that one? Should we be seeing your PC screen and not the lab? All right, you should see both. Operator error there. Any other questions, John? Are you flagged?
Fine.
How do we design for multiple outputs for a flyback converter? That's a really good question. So you have to decide how much power is coming off each output, and it is absolutely crucial where you put the windings relative to each other if you want to get good regulation and good performance. So in that case, I know what the rules are for where to put them. But in the lab, I will build many, many transformers. So if I have 3 or 4 outputs, I'm going to try and rearrange those outputs in a lot of different ways to find out which one gives me the best cross-regulation. Okay, there is no simulation of that. There is no analysis of that. It's too complex. It's too nonlinear to figure out exactly how that cross-regulation is going to work. You won't find any papers on cross-regulation of flybacks for that reason, because you can't analyze it. So if you can't analyze it, universities aren't interested in it. If they can't write equations and prove their equation is right, interest is gone. So there's very little written about cross-regulation on things like flybacks. But yeah, all of us, we have to do multiple output flybacks. Lots of the app notes that you see out there are not designed for good cross-regulation. They're designed for other things like different EMI signatures. Okay, so a lot of flyback app notes I see, they are not the way I would wind it. And there's too much there to get into in this session. We spend quite a long time with that in our workshop. We have a couple of slides dealing with that, talking about that in detail. How you can move the windings and get different cross-regulation on outputs. Anything else? Which secondary do I use for the feedback control? Whichever one you want to use. If you get good cross-regulation, you can use any or either. If you've got multiple ones, which is the one that needs the tightest regulation, that's the one that you can use for feedback. If you don't need really tight regulation, well, use the primary bias winding for the feedback. Then you don't need an optocoupler. So everybody's situation is different on which one gets used for the feedback winding.
Guys persisting on about the regulation between the windings, just say you have to come to the webinar to that rule.
Where's the question? Down the bottom?
Yeah.
Is there any hard rule for regulation winding multiple output transformer? No. Sorry. Is there a maximum number of outputs on a single transformer you have designed? Yes, it's determined by how many pins are on the bobbin. Sorry to be facetious here, but that's it. You can. I've done 5 output transformers with forwards, 5 output transformers with flybacks, and you just run out of pins after a while, so you have to use a bigger one, bigger bobbin. And in magnetics, there's no hard rules on anything except for, this is important, we'll finish up on this point here. When you're designing a flyback, you're designing an inductor, there's one hard rule. And the one hard rule is don't saturate this equation. Don't violate this equation. Same on transformers, there's a similar equation for transformers. Now, here's the funny quirk in our industry. If you buy an off-the-shelf transformer, off-the-shelf flyback, just about all the off-the-shelf flybacks will not tell you what the turns count is. They will not tell you what the area of the core is. So you have no worst case analysis. You have to dig in and get that information. Okay, but this is the one hard and fast rule. Don't saturate your magnetic, ever. Because if you do, it's a catastrophe. Things blow up, they fail, you know, your product doesn't work anymore. Everything else is variable. Okay, you can move the windings, you can shift the windings around, you can shift the turns counts around, you can wind it left to right, right to left, you can flip things, you can use Litz wire, you can try so many different variations in here. And you get to the point, it's like, well, what is the fastest way to do this? You know, should I be using finite element methods, or if it's a little flyback, should I just build it and see which one works? For me, it's clear. You build and test, you know, with intelligent steering of the design, and then that comes out much quicker than trying to just analyze it. I mean, so many students these days, so many papers just want to analyze, rather than designing quickly, testing, say, okay, there we are. That's what industry does. Okay, so lots of this stuff, you know, defies good analysis. Okay. All right. Anything else, John? Looks like that.
Some of them are not archery.
How does the manufacturer? Okay, you got that one. Lost audio. It's oh, possible reasons for the hissing noise in the transformer. I think I covered that because our circuit had a little bit of hiss. It's when you see that jitter, you got to go probe the waveforms, and you're going to see jitter somewhere. You're going to see hissing is sound of chaos in your converter. So when it goes into a chaotic operation, that's when it's going to hiss at you. So you're switching at 200 kilohertz, but that hissing noise will create low frequency harmonics that you hear, and they're going to be sporadic and all over the place. That's why you hear hiss. Hiss means white noise. White noise means you got lots of frequency components in it. It's very common in a flyback. All flybacks should be current mode. I mean, all flybacks should be current mode. Otherwise, you can't design the inductor. You turn on the switch. The initial spike of the current sense hits the comparator because it's down at light load, and then it trips it. And then the next time it trips it somewhere slightly different, and then somewhere slightly different, because you're just on that noise threshold. So it's just jumping around. It's putting out chaotic random noise. Sometimes you hear it, sometimes you don't. Once you part your magnetics, glue them all together, you know, you've got to stop the windings from moving. Okay, a flyback transformer is built like a speaker coil. It's supposed to make a noise when you excite it. That's what it's for. So if anything can move, it's going to move. So stop it moving, just stop it hissing. Okay, but you try to clean up the waveforms first to stop that sporadic operation. Very often you can't do that. So hopefully that answers that question. What else you got, John? Oh gosh, here we go. Books often show NP equals V over 4.4. Stop reading books on magnetics, okay? They work in the wrong units. They don't work in Tesla. They work in Ørsteds and other things. And 4 factor, no, I have no factor of 4 in there. He says, should NP be V over 4?
I answered that question.
Yeah.
So just stick to SI units.
Yeah, you stick to SI units. There's 2 equations, and that's all you need to know. It's not that complicated, but it is experience. I mean, I make this look easy, but I've done a flyback, you know, 1,000 times in my life, you know, but when you get down to doing it that many times, you realize the simplicity of doing it, and then the different options of windings are what's important. But it's really really important to recognize that just don't believe everything you read here. When you read some of the app notes from some of the big semiconductor companies, they tell you to wind the transformer the worst way for cross-regulation, the worst way, okay? Because they're thinking about something else. Doesn't mean it's a bad transformer, they just have a different objective. Most of us designing custom grid, we have a specific cross-regulation objective. So don't believe everything you read, just get in the lab and start doing it. And just because it's from a big name company who will disagree with me, you know, don't say, well, they're probably right because they're a big name company. It's like, no, they're semiconductor companies. They're selling you chips, okay? They do a great job on chips, but they're not necessarily magnetics designers. There's some good magnetics designers, but their objectives are different to what your objectives are going to be. So you've got to get into this and learn this yourself. But hey, it's a good thing, you know. If you don't design and play with magnetics, what else is there to play with these days? I mean, everything's integrated, everything's on a card. You know, magnetics is your playground. It's where you can do a lot of changes and make things really cool by changing the way magnetics work. So learn your magnetics. Any of you students out there, if you can go to an interview saying that you have used you've built and you've wound and you've tested magnetics, you have a job. You have a job. All right, the cards add a fair amount of stray inductance. You're looking at our board here layout, right? Tony Selsick asked that. So these cards, you've got things well spaced. It doesn't matter because the board layout is very tight. We're canceling everything when we go down to the board. Everything that's crucial is on the card. So bypass caps. So here on our board, we see the output caps, and then we see the diode rectifier card is here. They're separated by a long way. Hidden away on that diode rectifier card, I don't know if you can see that, is a cap. Okay, so the tight loops are all closed on our test boards here. Same on the switchboard. Okay, so every spacing on this board that's long is an inductive spacing. Okay, so it doesn't matter how far the cards are away. So we could run this board at 500 kilohertz or a megahertz, and it would be fine. Okay, the parasites do not get in the way.
What's the maximum voltage we can measure on the box?
200 volts with a 10 times probe and 2000 volts with a 100 times probe.
Repeat the questions.
Oh, what's the maximum voltage on the Ridley box? You can look up the specs for the scope. And let's go look at the scales here. And let's see, you see right there, you can do plus or minus 200 volts with a 10 times probe. But you know, it's the same for every scope has that limitation. I don't think you could do more than 200 with maybe it's 400 on some of the scopes, but they all run out of steam. So you just took up a times 10 times 100 probe, and then you've got the extra voltage range on there. So if you think about it, you know, we like to think of a scope as working with really high voltages, but no, it counts on the divider first. You can't just put a one-to-one probe. And I think this one is protected at a couple of hundred volts before you can blow it up. So, you know, it's a really good functional scope. We run our labs off the scope now just because they're so much more mobile. Okay, any others? Ring coil tester. That's the same thing about, you measure the frequency response. Zoom, we're not going to use Zoom. Lots of reasons for that. It just, you know, it's okay. A dual flyback, you shouldn't need a snubber. Okay, I see lots of app notes where they don't put snubbers on the secondary diode. They say, okay, we're going to go discontinuous mode, so the secondary is going to naturally commutate. What about in a transient? During a transient, you'll be hard switching that secondary rectifier. When you do that, the ringing can either destroy the part, or that ringing get into your controller and you're going to get into some strange burst mode. Maybe it'll start hissing. If your converter is hissing, it might be because you don't have your snubbers in place. You look at the waveforms on the screen right now, you know, we don't have all our, oops, sorry. We don't have our snubbers in place here on the primary side, so we haven't taken care of this ringing. This will affect things. Okay, so even though you don't need it for stress, you damp the ringing because it will come and get you either audibly or in the EMI signature when you move on to that part of the design. Okay, resistors, you got that. Anything unanswered, John?
Blue one now about the really.
Somebody asked if they can.
How can you buy the board? It would cost way too much. We'd have to sell it to you for about $100,000 for all the investment we put in it. So we're working on that. We're trying to decide what to do about that because, of course, you know, this is our test bed. This is how we work. We've got a very proprietary, very well-designed board here. We use it for our consulting jobs. It's really powerful. So I know why you want it, okay? But we haven't quite worked out how to sell the boards without losing control of the boards, because this is a potent design tool. You know, we expect to be able to prototype, you know, anything up to a few hundred watts converters in about a week's work on this board. Okay, so we're way ahead of, you know, anybody that doesn't have this kind of test bed. So it's a really powerful thing, and we're trying to figure out, yeah. What we would love is big company came to us, hey, we love your test bed. We'd like to buy into that. They give us enough money that we let everybody have this board, and then the whole industry would take a huge leap forward. Everybody would be able to prototype like we do. But everybody wants to buy the board for $50, so that's not happening now. So maybe one day one of the big companies will say, yeah, I like your prototyping systems, and we're going to invest in that, and then we're happy. So we've got some big companies here. If anybody is interested in this, you know, wants to sponsor this, sure, come talk to us. It takes a long time to read through your questions here. So I think it's 11:30. We've got lots of people here. Let me just to finish up with our sales pitch, of course. Not entirely sales pitch. You've already seen everything we do here. But Ridley Works, if you'd like a full demo as opposed to the demo that's on our website, send us an email. This will save you so much time in your work, you know, having Ridley Works. I don't know how anyone designs without it, quite honestly, but people like to go slow, some of them are by the hour, so that's good too. But we can help you have more fun by the hour. Design workshops, obviously we're on hold a little bit with those, but we have some things coming out, and hopefully next year we'll be back to in-person here, full on again. I know there's a lot of pent-up demand for that. And you get to see our new design boards as well, which is pretty cool. And frequency response analyzers, you've seen all about that. I've answered questions there. Please join our Facebook group, okay? Come to our Facebook group, click on that. And here you are in the Facebook group. Oh, sorry, I'm not logged in on this one. There's 4,500 members now. And you ask questions, you get good answers, okay? These are all working engineers. There's a book on Curl mode, you can download that. You can click on any of these links. All of these webinars are now available in our Power Supply Design Center. So we've got 7 in the series now. We'll be doing another one in about 3-4 weeks. So come to our Power Supply Design Center. And we've got about 30,000 people registered in our design center now. So this is a big community of people who are taking advantage of all this. And then, of course, we got all the specs on the Ridley box here. I don't see on the scope. Yeah, the peak voltage is not there, but you can go look at their, you know, the data sheet for this and find out the peak voltages on that. Okay. Please send us questions, comments, future titles for webinars. We'll see that in some of the comments here. We will go through all these afterwards and take a look if anyone wants to talk about what you'd like to see for future topics. And I think that's it for today. Everybody stay safe and have a good rest of your Thursday. Thank you.